Hello all, greetings of the day. Welcome to the online video tutorials on Module 1 ARM 32-bit Microcontroller. Course is Embedded System 18EC62. Myself, Akshit Monnapake, Assistant Professor, Department of Electronics and Communication Engineering, Sai Vidya Institute of Technology, Bangalore. In the previous lecture video, we discussed the concepts of microcontroller, microprocessor, its advantages and disadvantages, and embedded systems. We also discussed the concepts of ARM Cortex, background of the ARM, architectural versions, the thumb 2 technology, and some of the applications of Cortex M3 processors. Now let us discuss the architecture of Cortex M3 processor. So the Cortex M3 is a 32-bit microprocessor. It has 32-bit data path, a 32-bit register bank, and 32-bit memory interface. So the processor has a Harvard architecture, which means that it is having a separate instruction bus and separate data bus. This allows instructions and data access to take place at the same time, and as the result of this, the performance of the processor increases because data access do not affect the instruction pipeline. This feature results in multiple bus interfaces on Cortex M3, each with optimized usage and the ability to be used simultaneously. However, the instructions and data buses share the same memory space, which is also called as the unified memory system. In other words, you cannot get 8 GB of memory space just because you have separate bus interfaces. The Cortex M3 has a 32-bit register bank, out of which 13 general purpose registers, 2 stack pointers, a link register, a program counter, and a number of special registers including the program status register is available. So the Cortex M3 core contains a decoder for traditional thumb and the new thumb 2 instructions, an advanced ALU with the support for hardware multiply and divide, control logic, and interfaces to other components of the processor. It is the memory mapped system with a simple fixed memory map for up to 4 GB of addressable memory space with predefined dedicated addresses for code, SRAM, external memory devices, and internal external peripherals. There is also a special region to provide for vendor specific addressability. Now the memory protection unit, also called as the MPU, is an optional component of the Cortex M3 processor that can improve the reliability of an embedded system by protecting critical data used by the operating system from user applications. How is it done? By separating processing tasks, by disallowing access to each other's data, disabling access to memory regions, allowing memory regions to be defined as read-only, and detecting unexpected memory access that could potentially break the system. The highly configurable NVIC is an integral part of the Cortex M3 processor, and it provides the processor's outstanding interrupt handling abilities. It is standard implementation. It supplies a non-maskable interrupt and 32 general purpose physical interrupts with 8 levels of preemption priority. It can be configured to anywhere between 1 to 240 physical interrupts with up to 256 levels of priority through simple synthesis choices. The debug access into the Cortex M3 processor based system is through the debug access port that can be implemented as either a serial wired debug port or a 2-pin interface or a serial wired JTAG debug port that enables either JTAG or a serial wired protocol to be used. The Cortex M3 processor bus matrix connects the debug interface to the external buses. So the bus matrix also implements unaligned data access and bit banding. So the next topic is the operation modes. The ARM Cortex M3 processors has 2 operating modes and 2 privilege levels. The operating modes can be named as the thread mode and the handler mode, and the operating mode determines if the normal program or a exception handler is running in that particular processor. The privilege level are also of two types. One is the privilege level, the other one is the user level. So the privilege level mechanism is used for safeguarding the memory access to critical regions. So when a processor is running a main program which is in the thread mode, it can either have the privilege state or the user state, but the exception handlers only run in privilege state. Let us discuss the operation modes transitions. When process exits the reset, it is in thread mode with privileged access rights. In the privileged state, a program has access to all the memory ranges except when prohibited by the MPU settings and can use all the supported instructions. The software in the privileged access level can switch the program into the user access level using the control register. When the exception takes place, the processor will always switch back to the privileged state and return to the previous state when exiting the exception handler. A user program cannot change back to the privileged state by writing to the control register. It has to go through the exception handler that programs the control register to switch the processor back to the privileged access level when returning the thread mode. The separation of privileged and the user level improves the system reliability by preventing system configuration registers from being accessed or changed by untrusted programs. Built-in nested vector interrupt controller. The Cortex M3 processor includes an interrupt controller called as the nested vectored interrupt controller or the NVIC. It is closely coupled to the processor core and it provides a number of features which are listed below. The first one is nested interrupt support. So the NVIC provides nested interrupt support. All the external interrupts and most of the system exceptions can be programmed to different priority levels. Now when an interrupt occurs, the NVIC compares the priority of this interrupt to the current running priority level. If the priority of the new interrupt is higher than that of the current value, then the interrupt handler of the new interrupt will override the current running task. The next feature is the vectored interrupt support. The Cortex M3 processor has a vectored interrupt support. When an interrupt is accepted, the starting address of the interrupt service routine or the ISR is located from the vector table in the memory. There is no need to use software to determine and branch to the starting address of the ISR. Thus, it takes less time to process the interrupt request. Then we have the dynamic priority changes support. The priority levels of the interrupts can be changed by the software during the runtime. So the interrupts that are being serviced are blocked from further activation until the ISR is completed. So their priority can be changed without the risk of accidental re-entry. Then we have the reduction of interrupt latency. The Cortex M3 processor also includes a number of advanced features to lower the interrupt latency. Now these include automatic saving and restoring some register contents, reducing the delay in switching from one ISR to another, and handling the late arrival interrupts. And the last feature provided by this particular NVIC is the interrupt masking. So interrupts and system exceptions can be masked based on their priority level or can be masked completely using the interrupt masking registers, that is the base PRI mask and the fault mask. They can be used to ensure that the time critical tasks can be finished on time without being interrupted. Memory map of Cortex M3. The Cortex M3 has a predefined memory map. This allows the built-in peripherals such as the interrupt controller and the debug components to be accessed by simple memory access instructions. Thus, most system features are accessible using the C program code. The predefined memory map also allows the Cortex M3 processors to be highly optimized for speed and ease of integration in the system on chip or the SoC designs. The Cortex M3 design has an internal bus interface optimized for this memory usage. In addition, the design allows these memory regions to be used differently. For example, the data memory can still be put into the code region and the program code can be executed from the external RAM region. So as you can see the diagram, the memory map has different segmentations: the code, the SRAM, the peripherals, the external RAM, the external device, and the system level memory. So the system level memory has all the important features which stores the built-in interrupt controller or the NVIC, the MPU control registers, and the debug components. The next topic is the bus interface. There are several bus interfaces on Cortex-M3 processors. They allow the Cortex-M3 to carry instruction fetches and data access at the same time. The main bus interfaces are the code memory bus, the system bus, and the private peripheral bus. The code memory region access is carried out on the code memory bus, which physically consists of two buses, one called the I code, the other called the D code. These are optimized for instruction fetches for best instruction execution speed. The system bus is used to access the memory and peripherals. This provides access to the static random access memory, peripherals, external RAM, external devices, and also a part of the system level memory region. The memory protection unit, also abbreviated as MPU. This is optional to the Cortex-M3 processor. It allows the access rules to be set up for privileged access and user program access. When access rule is violated, the fault exception is generated and the fault exception handler will be able to analyze the problem and correct it if possible. In common scenarios, the operating system can set up the MPU to protect the data used by the OS kernel or the operating system kernel and other privileged processes to be protected from the untrusted user programs. The MPU can also be used to make the memory regions read-only. This prevents the accidental erasing of data or to isolate the memory regions between different tasks in multitasking systems. So thus this makes the system most robust and reliable. Let us discuss the instruction set of Cortex-M3. The Cortex-M3 supports the thumb 2 instruction set. This is one of the most important features of the Cortex-M3 processor because it allows the 32-bit instructions and the 16-bit instructions to be used together for high code density and higher efficiency. It is flexible and powerful, yet easy to use. In the previous ARM processors, the central processing unit or the CPU has two operations, a 32-bit ARM operation and the 16-bit thumb operation. In the ARM state, the instructions are 32-bit and can execute all supported instructions with high performance. In the thumb state, the instructions are 16-bit, so there is a much higher instruction code density, but the thumb state does not have all the functionality of the ARM instructions and may require more instructions to complete certain type of operations. So to get the best of both, many applications mix the ARM and the thumb codes, but this results in an overhead. The overhead has the execution time and the instruction space to switch between the states. ARM and thumb codes might need to be compiled separately in different files, thus increasing the complexity of the software development, and it also reduces the maximum efficiency of the CPU core. With the thumb 2 instruction set, it is possible to handle all the processing requirements in one operation state. Note that the Cortex-M3 processor does not support the ARM codes, and previously all the exceptions were handled in the ARM state of the microprocessors. The Cortex-M3 processor has a number of advantages over the traditional ARM processors, such as no state switching overhead, saving both the execution time and the instruction space. No need to separate the ARM code and the thumb code source files, making the software development and maintenance easier. It's easier to get the best efficiency and performance, in turn making it easier to write software because there is no need to worry about switching codes between the arm and the thumb to try to get the best code density as well as the performance. The next topic is the interrupts and exceptions. The Cortex-M3 processor implements a new exception model introduced in the ARM version 7 M architecture. So this exception model differs from the traditional ARM exception model, enabling very efficient exception handling. It has a number of system exceptions plus a number of external interrupt requests, which are external interrupt inputs. There is no fast interrupts or the FIQs which were present in the previous versions of ARM in this particular Cortex-M3. However, the interrupt priority handling and the nested interrupt support are now included in the interrupt architecture. Therefore, it is easy to set up a system that supports the nested interrupts. That is, a higher priority interrupt can override or preempt the lower priority interrupt handler, and that behaves just like the FIQ in the traditional ARM processors. So this table represents some of the exceptions which are present in the Cortex-M3 processors. It has the exception numbers, the exception types, the priorities and the description of the exceptions as shown in the table. The next concept is the debugging support. The Cortex-M3 processor includes a number of debugging features such as the program execution controls, including the halting and stepping, instruction breakpoints, data watch points, registers and memory accesses, profiling and tracing or traces. The debugging hardware of the Cortex-M3 processor is based on the core site architecture. Unlike the traditional ARM processors, the CPU core itself does not have a joint test action group or the JTAG interface. Instead, a debug interface module is decoupled from the core and a bus interface called as the debug access port or the DAP is provided at the core level. Through this bus interface, the external debuggers can access the control registers to debug hardware as well as system memory even when the processor is running. The control of this bus interface is carried out by the debug port or the DP device. The debug ports currently available are the serial wired JTAG debug port SWJDP, which supports the traditional JTAG protocol as well as the serial wired protocol, or the SWDP, which supports only the serial wired protocol. The JTAG DP module from the ARM core site product family can also be used. The chip manufacturers can choose to attach one of these DP modules to provide the debug interface. The chip manufacturers can also include an embedded trace macro cell ETM to allow instruction trace. The trace information is output via the trace port interface unit or the TPIU, and the debug host, usually the personal computer, can then collect the executed instruction information via the external trace capturing hardware. Thank you for watching this video. I will see you all in the next online video tutorial of ARM 32-bit microcontrollers.